Hello everyone, this is Mr. Kaviani, and by the end of this video you should be able to explain what work is and calculate the work done on an object in various scenarios. Work can be defined as a change in the energy of a system due to an external force. Work, just like energy, is measured in joules, and this is because work is nothing more than a change in energy. And therefore, because energy is a scalar quantity, work is also a scalar quantity, meaning work does not have a direction. It's also important to note that because work is a change in energy, work can be positive or negative. Positive work would indicate that an object or system is getting energy, and negative work would indicate that an object or system is losing energy. To derive the formula for the work equation, let's take a look at the lawnmower image to the right. Let's say that you're mowing your lawn and you exert an applied force F downward at an angle on the handle of the lawnmower. And the lawnmower travels some displacement D horizontally along the ground to the right. To find the work that you did on that lawnmower, we would take the component of the force that is parallel to the displacement, or the piece of that applied force that is going in the same direction as the lawnmower is going. And we will multiply that by how far the lawnmower goes, or the lawnmower's displacement. So in other words, we can express the work done on an object by F cosine theta multiplied by the displacement d. So this F cosine theta term, that is the component of force in the direction of the object's displacement. And in this case, theta happens to be this angle measured between the displacement vector and the force vector. So if you consider F here, the applied force, to be the hypotenuse of its own triangle, right? This leg of the triangle would be F multiplied by cosine of that theta angle between the displacement and the direction of the applied force. This gives us the component of force parallel to the displacement. We will take a look at some examples in a later video. Before we look at some examples of calculating work, it's important to first define what a system is. Work changes the energy of a system, and a system is nothing more than a collection of objects. When we solved problems involving connected masses in a previous unit, we considered the two masses and the string connecting them to be a system, or a collection of objects that we were interested in. And we drew a red dashed line around them to indicate a system boundary, or in other words, everything inside the dashed line was our system, and everything outside of the dashed line, all of the other objects, were the surroundings. So in this example, the pulley itself, the ceiling, the air molecules were not part of the system, they were all part of the surroundings. Work changes the system's total energy. So in other words, work is able to change how much energy a system has, or this collection of objects has. If there is no change in the total energy, then there's no work being done. What that means is, and we'll see this in much more detail later, that you can turn one form of energy into another form of energy inside a system. But as long as the total amount of energy is not changing, there's no work being done. So how do you choose what your system is, right? Like, why did we choose these two blocks and a string? Why didn't we choose the pulley? Well, you have to ask yourself, what are you trying to solve? In many cases, if you're asked to solve for a certain variable, you'll need to include the object to which that variable is related in your system. Another important question to ask when choosing a system is, what's going to make this problem easier to solve or even possible? For example, in this scenario to the right, we did not include the pulley in our system because the pulley itself was not moving or accelerating. And so it made analyzing the system much more difficult. By leaving the pulley out of our system, we were able to solve this problem much more easily. So when you're asked to solve a problem involving energy transformations or a system, it's important to take a moment and think about which objects would make sense to include in the system and which objects would make sense to leave out. All right, the last point we need to make about work before we look at some example problems is what it means for there to be positive work and what it means for there to be negative work, right? Work is a change in energy. So the sign of work tells us if the system that we're looking at is getting more energy or is losing energy. So in the case of positive work means there's a positive change in the energy of a system. That means the system has more energy after work was done than it did before. Negative work, on the other hand, means that there was a negative change in the total energy of the system. That means that the system has less energy at the end after work was done to it than it did before. Let's see how the work equation captures this idea. In the upper right-hand corner of this slide, I have a box being pushed to the right. I've shown an applied force arrow to the right and also the displacement arrow indicating that the box is also traveling to the right as that force is being applied to it. So if we look at the work equation, right, work is equal to that component of force parallel to the displacement multiplied by the displacement, right? But if you look at the force applied vector and the displacement vector, right, what is the angle between these two vectors? Well, there isn't one, right? They're pointing in the exact same direction. And so theta here is going to be 0 degrees, right? There is no difference in angle between two arrows pointing in the same direction. So this ends up just being f cosine 0 times d, and that just gives us f times d, right? So positive. So anytime theta is less than 90 degrees, then that means our work is going to be positive, right? Anytime that the force is being applied in the same direction the object is traveling in, then we have positive work. Now, in the other hand, for the case of negative work, you can imagine in this diagram in the bottom right that there is a box that has been pushed and it's sliding across the floor, right? So this box is sliding across the floor and there's some force of friction. We'll change this to friction, actually. That makes a bit more sense. So the box is still traveling to the right, so it still has a displacement in the direction that is right, but there's one force acting on it to the left, and that is friction at this point. It's going to eventually slow down and stop. So in this case, the angle between friction and the displacement vector, if you show them exactly in the same plane here, this is the displacement, and this is the force of friction. What's the angle between these two vectors? Right, they're both vectors. That's going to be 180 degrees, right? Friction is opposite, directly opposite the displacement. So the angle between them is 180 degrees, or half of a circle. So cosine of 180 degrees, right, is -1. And so the work here, if it's f cosine theta times the displacement, that's just going to be negative f times d, right? Cosine theta goes to -1. And so you see here, this negative sign indicates that the force acting on the object is in the opposite direction that the object is moving. So to summarize, when a force is being applied in the same direction as the displacement, work is positive. When a force is being applied in the opposite direction of an object's displacement, then that means the work done is negative.